Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks, Shen. I'm here primarily representing IMS, but in particular, I'm subbing for Ben Yu, who had intended to come but couldn't make it because of some personal issues. And what she sent me were some slides that were based on her presidential address from IMS last year that she delivered in Sydney. And the title of her address was "Let Us Own Data Science." I thought it was "Let's Own Data Science," but I think she uncontracted "let" and "us." And "us," I think, here represents statistics. It was an address to the Institute of Mathematical Statistics, so in the audience were statisticians and probabilists. And this was not a group that you really needed to convince about ownership of data science. It's kind of a sensitive issue in terms of the terminology there. Her address is described in the IMS bulletin, so you can have a look at that if you wish at some point. But in her slides, she goes through the different connections of bridging computer science with math and stat and domain side part knowledge. I don't want to spend too much time going through her slides. I want to really get to what I wanted to say this thing, but I feel obligated since I'm subbing for her to at least present her slides a bit. She did want to thank Jennifer Shays and especially thanks to the conference committee, David and Sham, who helped organize this. She mentioned a couple people in her presentation, and I was more interested in how she crafted this presentation because I have to give the president's address next year. And so I like the way she did it. So she started talking about this guy Carver. Carver was the first editor of the Annals of Statistics, probably in the 1930s sometime. And there's a quote from Carver about upgrading from logarithms to tabulating machines, which is kind of a nice one. Logarithms must be considered now as a tool of the past. This is hard to believe, right? Present-day commercial institutions almost without exception use computing machines rather than logarithms in the conduct of their business and interests of efficiency in both time and labor. She also mentioned the Hollerith tabulating machine, HTM, and I hadn't realized that this guy started a company. He was the founder of the tabulating machine company, which eventually became IBM. And the first supercomputer he delivered to a university, I didn't know this either, was to Columbia in 1931, and that's the time when they used the words, maybe the first time in a newspaper, supercomputing, which is also an interesting twist on it. The other person that she mentioned was Helen Turner. So this was a address given in Sydney, and Helen was the first president of the Australian Statistical Association, and she also did very kind of broad research in she was experimental scientist. She did methods in breeding, and she was a good communicator. So these were all kind of components that might go into what makes up a data scientist. So she added Turner and Carver together and called this the kind of prototype of a data scientist. And putting these traits together, she had these 5 traits: statistics, domain science, knowledge, computing, collaboration, and communication to outsiders. And then this is the part I didn't get at all, actually. Is there something I'm missing here? She said data science equals SDC cubed.
I think it's just multiplying the stuff.
I got that, but I thought there was some other deeper meaning than that this really meant something special, but I guess you read it the same way I do. Anyway, and then she wanted you to enjoy the conference, which I do too, as well. But I wanted to get to the main point, which was the next slide. So I'm going a little bit off the format she wanted me to adhere to, but I wanted to go forward in talking about a connection between IMS and data science. What can we do to kind of facilitate this interaction and to be more embracing of the society to data science? They don't fit so naturally necessarily, and there's a lot of young scientists now, young statisticians are coming out who are working in the data that were out there, just maybe for discussion at a later time, but some things just to think about, and I think probably many of you are already considering these aspects. And one is IMS has a provision for having a subgroups under the IMS auspices, and right now there's only 2 subgroups. One is in finance, and this finance group is really a little bit, maybe a little bit like data science, that is not completely under the umbrella of IMS. A lot of the finance people are in probability, and probability sometimes falls under mathematics, maybe more comfortable in mathematics. But there is this finance group, and they organize a conference every year under the IMS auspices. So this is something I think would be a good idea. I think once you have a data science group within IMS, it gives it a bit more visibility, and they could interact with also junior members and create sort of an identity under IMS. The next one is we should plan for the next IMS data science meeting. And the question is, how should this evolve? Maybe IMS plus blank. I wasn't sure who would be, if Microsoft would be permanently in there, or if it would be someone else as well. But we should think about the next one. And I think this also maybe coincides with this forming a data science group, that this could be a group that sort of organizes this annual meeting. So I think this is something we should consider. I'm happy to do this in New York next year, and I think there's some industries that in New York, including Microsoft, that we could collaborate with. But I think there's also an opportunity to bring together universities and data science and industry. So New York is a good place for it, but there are other departments besides Columbia in New York. It could be Duke, Carnegie Mellon, Chicago, and of course the West Coast in the Bay Area. So I think this could be sort of a prototype that we ought to think about doing every year on an annual basis. One of the sensitive issues, I think, as I understand it, is this one. I don't know if, is data science, establish data science publication outlets in IMS. And data science moves quickly. They like to do abstracts, short papers, whatever, and these are not always well received in the IMS journals. So what do we do about this? So I think we ought to really think hard about doing this. One is in, the Annals of Applied Stat, that area editors possibly that just handle data science, but I don't think that doesn't do everything, right? That's not enough. And should we think about, what are the other possibilities? I don't want to propose another journal or whatever, but maybe that is something we could consider. We need to think about this, and I think this is sort of an important issue, but you also have to understand the other side of it too, from the probability and statistics folks, the theory and the applied people, where they have to be kind of on board as well with that. So this is something that we could discuss here, but we should have a group that thinks about it and put a proposal forward to IMS. I think Ben and I are very supportive of trying to figure out something, and there's only a short window when Ben and I have maybe some influence in IMS. So let's not lose that opportunity. And then just other ideas are very much welcome to how we can incorporate data science as a group under the umbrella of IMS. I think IMS is a great organization. If you're not familiar with it, it's really one of the largest professional societies for probability and statistics in the world. And whenever IMS does something like start a new journal, it instantly becomes the best journal in the field. It doesn't take long. There's no lag, really. It's just they have very, very good people. They put in as editors, associate editors, and the quality becomes instantly top-notch. So it's a good, I hope this is a win-win. It's good for IMS to broaden its reach, and it's also good for people working in data science to be part of this organization. And there are many things that IMS can do for data science as well. So I'll end there. I have 24 seconds left. I'm over by 24. It's red. So thank you. Okay.
So, hi, my name is Susan May, and I'm organizing the first session on search and social media. One of the really interesting things about search and social media is that they share some very interesting statistical and computational challenges. They have large P and N. If you look at a modern day web search engine, there are literally trillions of documents and billions of queries and users per day. The data is incredibly sparse. Most words don't occur in most documents. In social networks, most people are not connected to other people. And all of the both representations and interactions are not IID. Words are not independent. Query streams are not uniform over time. So just about every imaginable assumption from a reasonable statistical perspective is broken. What I want to focus on today, however, or what the speakers are going to focus on today, however, are two additional and unique challenges, I think, brought on by the fact that both search and social media have become, over the last decade, incredibly pervasive in people's lives. How many of you have searched in the last 24 hours? How many of you have checked Twitter or Facebook or some other, or email even as a kind of social media? These are really becoming core fabrics of people's lives. And so I think two of the interesting consequences of that are, first of all, that we now more than ever need to take into account the fact that people are interacting with these systems, adding a whole other dimension of variability that we need to represent and think about. And the second is, because these are large-scale web services, we can do experimentation at a scale and speed that have not been possible before. So the first two talks in this session are going to focus on more core information retrieval problems. Shangjai is going to lead off and talk about how he's reformulating information retrieval as really a kind of joint optimization between utility for people and efficiency of operations for retrieval systems. And Daphna Shahaf is going to talk about how we can use information in the process of sense-making. Essentially connecting the dots between seemingly unconnected objects. The last two talks are really going to be about experimental design. Leon Batu, who was at Microsoft and is now at Facebook, is going to talk about designing efficient experiments that enable us to make causal inferences from data. And Johan Ygnander is going to talk about the challenges in doing randomized experiments in the face of something like a social network where there are huge spillover effects. So we'll first talk about some of the core retrieval algorithms and then about some of the, I think, really interesting and challenging experimental conditions. So Shane, without further ado, take it away.
Okay, well, thanks, Sue. Let me make sure that I know how to use this. Does this work?
Yeah, we need to bring your slides up.
So is this, let me see if this, okay, good. This, okay, very good. Thanks for the opportunity. It's my great pleasure to be here to share my thought and my work with all of you. And I'm looking forward to all the interactions, discussions, and your presentations. So what I'm going to talk about today is just some thought about what future search engines might look like, in my opinion. And this view also is more general than just looking at search engines. It might generally include all kinds of intelligent systems that deal with a lot of data. Okay, so there's no need to read this long title. Let me just proceed with the presentation. The motivation is obviously how to harness big text data, which I think is a problem that you all are very familiar with. But I want to emphasize that text data is actually quite unique because it's produced by humans and it's meant to be consumed by humans. This is very different from the data collected from sensors. In some way, we can think about humans as subjective sensors that would look at the world and then report some information, and that's in the form of text, right? So in that sense, we could put all the data together. Obviously, text data is very important for many big data problems. Now, because it's produced by humans, it has encoded our knowledge. And think about literature, we have a lot of knowledge encoded there. And it also encodes our subjective opinions. So it has a lot of information about what we think about the entity, like a person or product. Right? So this means it's a very unique source for discovering some knowledge that we may not be easy to discover from other data sources. Of course, in general, we should combine all kinds of data. The second point is that because it's meant to be digested by humans, then it has two consequences. One is that because there's so much data that no single person can possibly digest all the data, not even a small fraction of it. So we need tools to help us to digest the data. That's why many hands were raised when to ask the question whether you search it in Google or Bing, right? Now, the second consequence is that the humans must be in the loop in mining big text data because humans are the most intelligent systems in some sense to digest text data. Machines can help humans, but we can't just completely rely on machines or not yet. So since I'm going to talk more about the information retrieval, and then this whole session is about information retrieval, so I want to emphasize that information retrieval plays a very important role in big text data applications in general. So this shows a rough pipeline or logic pipeline of mining big text data. You start with a lot of raw data, and then you try to zoom into a small amount of very relevant text data that's actually needed for a particular problem. So we have this process of reducing the size of the data. This is the most effective way of solving the scalability problem. And then we're going to use techniques that we often call text mining to further analyze a small amount of text data to get the knowledge out, to support the decision making, support a lot of applications. So we're going to turn the data into actionable knowledge, right? Now, as I said, users are very important for any of these applications. And in fact, the users are generally involved in all these stages. Of course, what I'm going to talk about is more about search. But one important point, which was also mentioned in Sue's introduction, is that we need to optimize the combination of humans and the machines. So it's an overall global optimization problem. And in contrast, I think today we have paid a lot of attention to ask the machines to do as much as it can. This is good, but then we also need to think about opportunities of engaging humans effectively to solve the problem. And that setup turns out to also raise a lot of interesting questions for interactions between statisticians and machine learning researchers, and computer science, and many others, as you will see later. Okay, so I can skip this slide because you already know that, but perhaps you don't know that we sometimes need to search for even small data, like desktop search, which is really big for a particular person. Now here, I should mention that this was pioneered by Sue and her colleagues in Microsoft. So that's a very useful service that a lot of people are using, right? And the second point is search accuracy matters. Now, I meant to ask you to guess how many queries these search engines receive, but that's not actually the point. It's a lot. And the point here is that if you can save even 1 second or a few seconds or a minute for these queries, then you can save a lot of time. And obviously, there are many applications. So I have to say that I really would like to put Bing here. And I know Bing is getting a lot of queries. Unfortunately, I couldn't find the data point. So I have to say that it's not because I, just...
Between Google and Twitter.
Yes, it's somewhere here, right? So, I couldn't.
contrast, the first web search engine 20 years ago had 1,000 queries a day. So we have come an amazing way in 20 years.
Yeah. That's right. So from this source, I couldn't find the number of queries Bing is receiving. Anyway, so the central question that I'm going to address in this talk is, how can we optimize all these search engines in a general way? Because if we can do that, even if it's a small amount, then the benefit is huge. But this question is really ill-defined because we have not really defined what is exactly the search engine, although in our minds we know what the search engine looks like. Right? But if you think about it more, you may discover that perhaps it's not so simple. And also, of course, what is the optimal search engine? And how do we find or develop such a search engine? So let's start with the current search engine. And this is an overly simplified view of the current search engines. You have a query, and then the system, the search engine would match the query with the documents, and then return a ranked list, pi here. And inside the engine, typically you use some retrieval models to generate a lot of features to tell us which document is likely relevant. And then we use pretty much minimum NLP, although, as you mentioned, we want to actually use more to go beyond the current state of that, because understanding the text content is obviously very important. I think definitely is going to talk a little bit about that. But overall, we're going to use the machine learning as an umbrella to put everything together, or statistical learning. And then this would give us an optimal scoring function that can generate the score for each document, and then we're going to rank based on that. So if you look at this picture, our definition is basically the search engine is to return a ranked list with 10 blue links typically, and then basically our goal is to optimize this scoring function. And our objective function is typically based on the errors or quality of ranking on some training data set that we collect. Now, the question being raised here is this really a good definition, or this is our best definition? Now, actually, there are many problems with this definition because documents actually depend on each other. The utility of document depends on other documents. If a user has already seen the same document, obviously, the next one, which is exactly the same, which will also have an identical score, would not be very useful. Sometimes pieces of information can be put together to answer a question that's collective relevance. And we can't really do this. So, well, this is easy to fix. Let's just optimize the whole ranked list. And people indeed did that, and they have used learning to rank to optimize the whole ranked list. Of course, the complexity is much higher now. But this does help solve these problems. But we can still ask the question, is this definition our best definition? Unfortunately, it's not, because here we have not really considered a lot of context of the users. When the user types in a query, it's not just a single query. There are past queries, history, context, a lot of information about the user. And we have to model the user more intelligently in order to serve the user better. Without considering such information, it's very hard to model this whole user. Right? And also, we can optimize the performance over the entire session, which is more important. Right? And that's why I have game theory in the title, and that's a hint for thinking about this whole thing as a game, and the task, user's task is really the ultimate goal, and we need to optimize the whole thing. But people realize these problems, so they have done a lot of work try to fix these problems, and this is not a complete list of all the existing work, and just a suggestion of some ways to fix the problem. So for example, what about the context of the user's particular past history, etc. Then people started implicit feedback, personalized search. In fact, again, Microsoft research has a lot of work there, and many other researchers did that as well, and Sue and I think Jamie and some other people have done work that I also listed here. Now, what about users? Well, there has been some work, mostly, again, in industry labs, Yahoo Labs, Google, I think Microsoft again. We tried to model these users' intent, so task to some extent can be also inferred. What about the optimization of performance over the entire session? And there has been work that started to address the problem. For example, active feedback, where we sacrifice the performance temporarily in hope of learning more about the user to optimize the overall return, right? By exploiting machine learning. And exploration trade-off is a problem here. And recently, people have also used partially observable Markov decision process, POMDB, to model session search. And these are all great efforts, and that bring us more toward an ideal situation where we model the users accurately and try to serve the users optimally. But the question that I raise here is, can we address these problems or model these problems, frame these problems in a unified way? And here the solution is, I think, a cooperative game framework. So this is not a zero-sum game. It's not a competition. The users and the machines are collaborating with each other. So there is a common objective here. So the process of retrieval can be regarded as a cooperative game playing. And the players are obviously the search engine systems and users. Let's think about a simple case where we have just one user and one search engine, right? So they make moves and they take turns. And depending on the application, if it's a search application, typically the user initiates the first move. The user types in the query. But there are also cases where recommended system can make the first move, or queryless search, that's again Sue did, is an example of using context to initiate search. And all these can be regarded as basically having users and systems to interact with each other. And I should also say, in recommended systems, there should be also follow-up explanation of the item. And this is very similar to search. Okay, so, and then for each move of the user, the system would respond with some move. But if you look at this, the current system in this way, and it's playing a very simple game here. Right? So think about what moves the user has today. Right? It's just mostly typing the query, clicking on a document, or scrolling down. Right? So pretty much limited to a few choices. And similarly, the system also doesn't do a lot of other moves, even though in research, people have proposed, for example, clustering search results. There are more alternative ways of displaying the results. But the practical systems today play a very simple game here. And this limits the utility of the current system. And one point that I want to make is we can think in this way by designing more moves based on data mining operators, machine learning algorithms, or other functions that we can develop and bring all these functions together, make them available to the user, and especially provide a task-specific support for user. Right? So what's the objective of this game? Well, the objective here is to optimize multiple factors. One is, of course, to help the user finish the task. And as I said multiple times, finishing the task or finding the information is the ultimate goal. Right? So the ranking accuracy for a particular query is only part of the game. Right? So we want to satisfy the user's information need, or in general, help the user complete the task. Then we want to also minimize two other factors. One is the overall effort from the user. That could be measured by the time, by how easy it is to use the system, is it cognitively very demanding, etc. Right? But there is another factor, that's the system side, which can be measured by system performance requirement or resource requirement. Right? Or you can also measure this by the budget that you have, because you can invest in other ways to improve the system. Right? So, but you get the point, right? So we can have variants of formulating this problem. So, for example, one realistic setup could be given a constant effort of user. A user has just a few minutes to find the information, right? Subject to the constraint of system resources, we only have so much computing power that can be allocated for this user. Now, how can we maximize the utility of delivering information to the user? In general, these factors must be brought together, and that's the main point here. So there are some important benefits of framing the search problem in this way. The first is we naturally optimize performance on an entire session instead of on a single query. And this is like to optimizing the chance of winning the whole game. Now, if you play chess, then you will realize sometimes you want to sacrifice a piece. Right? And from a local viewpoint, this is not good. You're losing a queen. That's not good. That's not the game. But if you look at the whole game plan, it helps you win the game. So in search, it turns out that we need to do something similar, and it's possible to do something similar. Let me give you one example. So sometimes the user's query is ambiguous. Let's say Jaguar could be a car or could be an animal. Now, if the user doesn't find the information, the system doesn't perform well for such a query, instead of asking the users to repeatedly reformulate the query and keeping the ambiguity, you could have asked, did you mean jaguar by car or animal? Now, in such a case, the effort from the user side is not that much. The user would just click on one of them, but it would help the system tremendously. But note that in this case, the utility that we deliver to the user is almost zero, because we did not deliver any relevant information. It's probably worse than if you just guess what Jaguar means, and you would deliver some information. So in this sense, it's a little bit like sacrificing a piece. But as we learn from the user more, then the benefit will come in the later stages of interaction, just like winning a game. Okay. The second point is that we want to optimize. It suggests the optimization of the collaboration of the two parties, the users and the system. And this is to leverage the intelligence of both. Right. So, for example, a user would know well about what's important, what's useful, but the user doesn't know what information exists in the information space. The system is in the opposite direction. The system knows very well about what data we have, but the system doesn't know what you're looking for. So a natural solution would be to preview what information is related to your query and then let the user guide you to go to the right direction in the information space, right? So this is along that direction, and this kind of optimization can be addressed by using such a way to think about the search problem. And finally, it removes the boundary between a search system and a task support system. And as you will see more clearly when I present something more formal, right, along this direction. Right? That is because when we think about the query as one action taken by the user, or scrolling it down or clicking on a document as one action, then we can generalize this to all other actions, clicking on any button or making any request. And so that's why this is more general. So let's look at the current search engine in this framework. Right, so this shows a search process that we are having today. We can think of this as a dialogue between the user and the search engine. The user enters query, that's the first move, A1, and the system would respond with some decision. So which information items to present, how to present, etc. Now, I have to say the current search engines only optimize the ranking of the list. They did not intend to optimize the display, for example, for information. Why 10 blue links, not 5? Why some items cannot have a larger space to display the information at the cost of other items? How do you optimize this, right? We missed some optimization point here, right? Opportunity. And then the system would decide to display some results for the user to look at, and then the user would then check, and then the system will go on. Now, this is within 25 minutes, is that right?
You have probably 4 minutes left to talk and 3 minutes.
Okay, so because I somehow registered as the amount of time left for talk. So I have to skip some of the points, and the slides are available, so people can look at that. Let me just proceed to how to formalize this problem, right? So to solve the problem in this way, we can formalize this problem. So we have these actions taken by the users, the responses taken by the system so far, and then the question is, what's the next response? Right? So this is all very general, and we put the context here and documents, and then we capture all these in as a history of what happened in the past. Like context gives information about the current. And then the problem of decision here is, given all the observed information, how can we choose the best response? Right? So again, sorry, I have to skip some of the slides, and I intentionally include more slides just for completeness and also reference for discussion. So you will see I skip some of these slides. So I skip some non-essential information. So to solve the problem, we can then use Bayesian decisions theory to frame the problem. Right? So the key is to introduce a formal variable M that stands for user model. And this captures everything that we want to know about the user for our decision problem. Obviously, this depends on the problems. Here, we are interested in finding information. So one essential element is the information need. We have to have a model for what the user is looking for. And we also should keep track of what the user has already seen, and reading level and a lot of other information. How much time do you think the user currently has, right? And then we introduce a loss function to capture our objective. and then we just choose the optimal response, okay? And this is a standard Bayesian decision theoretical framework. So here we see we have observed the data and we infer the user model, and then we minimize the space risk. Now, this, of course, computation is very complex, so there are challenges in scalability. One simple way to simplify this is to take a mode of the posterior as approximation of this integral, and then we're not going to do Bayesian, basically. Then this would lead to a two-step procedure for solving the problem. Essentially, we don't consider the uncertainty of models. So given a user action, and then we infer the model of the user, and then we choose the right action, and then the user would take another action. And we ideally would also model what the user would do for our results, right? So this is something that we currently don't do, and we infer another model, etc. Now, this framework is very general because we can model actions at different levels. If you define the action as a keystroke, then you have query completion as the best service in responding to such an action. But you can also define actions at high level, like this search session as one unit. And then you can model the user's task. The user is traveling, perhaps, right? And so we can further generalize this, obviously, to analysis operators. And these are all moves or task requests. So the key here is to have a user model here that can be regarded as a state of a Markov decision process, if you see the whole process. So that's why POM-DP is very relevant, and reinforcement learning is very relevant, because we won't observe these states, yet we want to learn that, so we have to indirectly learn these rules here. So the key questions here, perhaps the most important research questions here, would be how to define them and how to infer them. Now, this will probably be a very important slide to unite a lot of interests here. And here I show a lot of aspects about the user that we want to infer. And we observe two kinds of data from the user. One is content, one is the behavior data in search log. So there are two kinds of big data. And then we want to generally use generative models to model the data to recover some of the information about users. Now, I have some example work. I'm going to skip all these all the way to the end. We can talk about this later, using some regression model to uncover users' latent preferences and interest in reviews. Okay, so the general question suggested by this framework would be, first, how should we design that game? What are the moves, right? And how do we compute the optimal strategy? And how is this related to game theory? So does Nash equilibrium still matter here? It's based on a lot of assumptions that may not hold for our problem. Right? How to evaluate such a system is a big problem, and I'm glad that there will be other talks to address this problem. Right? So I want to talk about the one specific problem that clearly ties these two together. I know you need to stop me. After this slide, just one picture. Okay. And so, so this problem is the following. So if you never show a lowly ranked document to the user, then you would never know whether users would like that. So the question is, how do you show this document, and where do you do the experiment? And that, I'm sure, will be addressed later in some talks. So I'm going to skip this summary. I just promised you to show one slide. And that's to say that in order to build such a system, we need collaborations from all of us. So we have an interactive service system. And that looks like a typical search engine with response to users. And then we'll collect a lot of user interaction log. And it can also include a lot of big data from other places about users and documents. And then we obviously need a traditional retrieval. We need a game theory. We need a machine learning to analyze the data, NLP to understand the text and the content, and then human-computer interaction, even psychology to understand the users. But at the core, I think it's the statistical modeling, the probabilistic modeling, statistical analysis, and the optimization. And this will be related to all these fields. It has already been used in all these different fields in NLP and in machine learning. I think definitely is probably going to talk about some also, and then in other talks, you might see some of the things. I think with that, I just stop. Looking forward to collaborations. Thank you.
Thanks, Frank.
Sorry for leaving just 42 seconds by the clock.
I use, okay, so we have a few questions down here. Why don't you set up your slide? Do you have a few questions for Sean?
Yeah, so how do you actually measure utility? Or I mean, you had some experiments which you glossed over, but if you're going to measure utility,
yes.
Presumably it's more complicated than just,
Yes.
did you get the right answer?
Excellent question. I just removed the time and thought about that. And one approach is to use a system that can be application that's easy to measure. For example, MOOC, massive online education. You can measure the grades of students or learning performance to assess the improvement of your system. Did you teach the students more effectively by doing experiments? I think some of the talks later will address this problem better.
But in the context of like search engines, you're talking about what exactly do you think gives utility?
That would be a measure of the task, whether the user has solved the problem, whether the user is satisfied with this, how much time the user has spent. Right? So this and how much resource the system has used to.
As you're envisioning a setting where you have a problem and with some interactive setting where they're trying to solve the problem with queries or something?
Yeah, you need to measure all the three factors. And then maybe depending on applications, we might emphasize some factors more than others.
Okay, thanks, Chang. And it'll be great to continue these discussions during the next 2 days.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.